The three types of bonds we're going to be discussing in this class are shown to you across the top of the page as ionic, covalent, and metallic. We're going to fill this table in and compare and contrast the different properties of these three different types of bonds, which you're going to learn all about here in this particular unit. So the very first thing it talks about here again is the location of the electrons. Basically in an ionic bond, notice the word ionic comes from the word ion. They are charged atoms. So one is going to steal, which is the more electronegative of the atoms, has a stronger attraction for the electron. So it's going to steal, and it's going to take on a partial negative charge, like this little green thing right there. It's going to have a negative charge because, again, it stole and gained somebody else's electron. Now, the less electronegative of these two elements, in this case right here, the purple, you'll notice it has a little positive green. It's a cation. So it is positively charged because it lost and surrendered its electrons to the more electronegative of the pair. So again, there's going to be a transfer of electrons. One is going to take and the other one is going to lose. Therefore, you get a positive and negative attraction. What holds an ionic bond together is that electrostatic attraction from the opposite charges. That's an ionic bond. Again, ion is the root word, and that's a really big clue as to what's going on there. The next one we're going to talk about is the covalent bond. In a covalent bond, the electrons are shared. They are not stolen or given up. They are shared. So if they're shared equally, where the electrons are going around both nuclei equally, we call that a nonpolar covalent bond. The bond is very equal, and the electrons spend equal time around both atoms. If it is a unequal sharing, we call that a polar covalent, and you'll see that the electrons are going to spend a little bit more time over here. Notice again this partial negative and this partial positive. So the electrons will spend a significant more time around the negative. Well, it's a partial negative. It's not an ion. It's not charged, but it's going to spend a majority of time over here and just a little bit of time over on the partial positive side. That's called an unequal sharing or a polar covalent bond. So the electrons are shared, and because of that, they are bound together. The nuclei, the atoms are bound together because they're sharing together, okay? Again, it's different from an ionic, where one is stealing, which is more electronegative, and the other one is losing, which is less electronegative. The metallic bond is a very different kind of beast, if you will. The metallic bond basically is a interaction between neighboring metallic atoms. Basically, they have so many energy levels. They could have 4, 5, 6, 7 energy levels, and they have a lot of electrons, like tons of electrons. So these electrons are just all over the place. They're just basically so many, and the atoms are so big that the nuclei have a very hard time of holding on to their particular electrons. Therefore, what we call that is a sea of electrons, basically like an ocean of electrons. There's just so many electrons all over the place with these really big energy levels that the nuclei have a hard time holding on to. So the electrons can actually jump and move around quite a bit. This is one of the reasons why they conduct electricity so well. Again, electricity is the movement of electrons. And if electrons are not held very tightly by their nuclei and they can move, well, guess what? That conducts electricity very well. So again, the metallics are quite different because there's not really a bond per se. It's just that there are so many atoms, so many energy levels, so many electrons that the electrons can kind of move around. And that holds them together, but again, it really affords them a fantastic ability to conduct. Now, the particles involved, what we're talking about here are what types of elements bond to make these three different types of bonds. In an ionic, you have a metal plus a non-metal. Metal and a non-metal, you've got to memorize this. A metal and non-metals, remember metals are on the left side of the periodic table and your non-metals are on the upper right corner. If you have one of each, again, these are always going to ionize to become positive, these ionize to become negative. If you have positive and negative, metal, non-metal, that's going to be an ionic bond. So a metal and a non-metal. If you have a covalent bond, those are all non-metals. We have a non-metal bound by a sharing of electrons to another non-metal. Don't forget, hydrogen's a non-metal, even though it's in the top left corner, but a non-metal with a non-metal. Because they're both, if they were ionized, they'd be both negative, right? So therefore, they're not ions. They are not charged. Otherwise, they would repel each other. So they're not charged. They're not ions. They bond because they share their electrons. They have plenty of them, and they're going to share them together. In a metallic bond, not surprisingly, it's a metal and a metal. That's pretty obvious. Okay. Now, don't get this too confused with an alloy. An alloy, remember, is a mixture of metals. Let me just go ahead and put this over here, just so you guys remember, is a mixture of metals. This is where you basically melt two different types of metals together, and you just pour them, mix them, and let them solidify. That's a little bit different. That's just a mixture of metals. We're talking about metallic bonds, which actually holds the atoms together. Some examples of ionic. Some examples of ionic would be, of course, good old table salt, sodium chloride. We have things like potassium phosphate. There's tons of them, right? So notice again, we have a metal and a non-metal. Metal, non-metals, right? The metals go first. Metals go first. The non-metals go second. That's the way it always is. Metals go first. They're positively charged. The non-metals go second because they are the negatively charged, right? Basically the same order as the periodic table. The left, then the right. Metals followed by the non-metals, always, always, always for ionics. Again, the sodium would be positive, the chlorine would be negative, the potassium would be positive, the phosphate would be negative. Okay, oops, what's that? All right, so an example of a covalent bond, if you're going to be a nonpolar, which again is going to be equal sharing, that could be something like O2 or N2, basically two atoms that are equal that are sharing. If you have a polar, that could be something like hydrofluoric acid, HF, where the F is a much bigger atom than H. Therefore, again, it would be an unequal sharing. The electrons would spend the majority of the time that they're sharing around the F because it's more electronegative. All right, and then over here again, what we have is just an example of what a metal would look like. Remember, the key thing you guys need to know about them is they are a sea of electrons. That's a phrase you guys need to know, sea of electrons. All right, so bond strength, bond strength. Basically, I'm just going to put this in relative terms. I'm not going to give you guys an exact number that you need to memorize. But bond strength, these are very strong. Okay, in our bodies, these would be our bones and our teeth. We don't have many other ionic bonds in our bodies other than our bones and teeth. These would be things like rocks and stones, concrete, things like that. These are ionic bonds. Covalent, again, are fairly weak. These are things like our skin, hair, softer things like this, gases, of course, all sorts of things like this, liquids, gases, and softer things. Like the majority of the bonds in our bodies are covalent bonds, which is why we're kind of soft. Metallic, of course, are also strong. That's not surprising because, of course, they're metals, right? You guys already know that. Okay, let me clear this. I'm going to slide up to get to the next part so we could finish out this table. Okay. So the physical properties, again, you see right here the melting point and boiling point of these. So notice, again, this is a pretty high melting point, right? And the boiling point. Those are very, very hot. That is 8 times hotter than what it takes to boil water in order to melt sodium chloride. Here, if you guys notice, these are much, much less. Again, remember, because these are strong bonds, and these, of course, are weak bonds. So when you melt, you're basically changing the interactions between the atoms, which is causing them to go to the liquid state. So obviously, the ionics, having a higher melting point, higher boiling point, are a much stronger type of bond, whereas the weak covalents, 77 degrees, again, that is still very hot, but it's not boiling, right? For water, at least. And H2, negative 250 degrees Celsius. That's crazy, right? Okay, and then notice over here, copper and iron. Wow, 2,000 plus degrees. So this again tells you why they are a very strong bond, because it takes a crazy amount of heat in order to liquefy these particular metals, which again, why we smelt and we have those massive furnaces where they melt metals. You ever seen pictures of those? Those are pretty dang impressive. All right, state at room temperature. So these are going to be, of course, solid. Okay, remember, think of bones and teeth. These could be powders. They could be gases or liquids. I'm just going to put LIQ for short. Powders, gases, liquids, and other soft things like that. Again, think of like our skin, like I keep using that example. And state at room temperature for a metal, well, obviously it's a solid. Except there's one exception, of course, which is mercury, which is a liquid at room temperature. Other than mercury, obviously they're all solid at room temperature. All right, solubility in water, meaning can it dissolve in water? Ionics, yes, they will dissolve. Think of sodium chloride, right? This right here, this is table salt. It will dissolve in water. All ionics dissolve in water. Maybe not instantly, but they do eventually. Remember I said that rock and stones are ionic. Again, this is how the Grand Canyon formed. Water running over long periods of time do dissolve ionic compounds, which is why, again, water can cut through rock. It takes a long time, but it does happen. Whereas I put salt in water, it dissolves very quickly. Covalence, if it is polar, if it's a polar covalent, remember what that means is an unequal sharing of the electrons, then that is going to be a yes. They are going to dissolve in water. Okay, so polar covalents do dissolve in water, but non-polar, which is where you have an equal sharing of electrons, an equal sharing of electrons, they do not dissolve in water. Okay, that's for your covalence. If they're polar, which is an unequal sharing, they do dissolve. If it's non-polar, which is an equal, I want to say bias, that's not the right word, an unequal sharing, I'm sorry, I can't think of a better word, then those do not dissolve in water. And does metal dissolve in water? Of course not. Metal does not dissolve in water. Okay, conductivity of heat and electricity. Ionics, they do, but only when melted or molten, to use that word. And the word when, that would be better grammar. Only when molten or melted. In the solid state, if I take table salt, sprinkle some on the table, and try to measure it with a conductivity meter, it's not going to conduct at all. But if I put that salt into water, it's going to conduct very well. Okay? So again, this is kind of one of those little caveats you guys need to memorize. Kind of like this one right here. These ones are kind of like this, but not this. Those are something you need to pay attention to. So the conductivity of heat and electricity, again, in the solid state, they do not, but when you melt it, they do. Covalence, they do not conduct at all. And metals, of course, they conduct very well. Again, because remember that sea of electrons, they conduct very well, which is why we make wires out of metals. Okay, let's finish this out, this very bottom part right here, malleable. Malleable means it can be bent. The way I think about that is like, say you have a mallet, a hammer, and you're smashing on metal, it's going to bend, right? Of course. It's going to deform and change the shape because I'm smashing it with a mallet. So malleable means it's able to be bent. The reason why they're malleable, remember that sea of electrons? The nuclei of the atoms are not really held in a fixed position, even though it's, again, a solid, but they could slide and they could move past each other. And if you look at the large scale of that, then you're going to have a deformation of the shape of that, of that metal. So the atoms can slide or move. And again, that's going to cause a deformation of the shape because, again, that's why it bends. Okay? The atoms are not fixed in a position, which is a little bit ironic because you'd think it would be the other way around. But again, because there's so many electrons, they could kind of move. It may take a lot of work, I can't do it with my hand. I can't take a piece of metal and go, "Hurr," and just bend it. Well, unless it's thin enough, right? Okay, so ionic compounds are brittle. They're brittle, and again, brittle just means like if I was to hit it with a hammer, it's just going to turn into a powder, right? Like again, think of table salt. That's another ionic. If I hit it with a hammer gently, it's just going to pulverize it into little tiny crystals, a powder. That is because the structure is a crystal. So ionic compounds, if you were to shrink down small enough and you were to look at an ionic compound, it's basically has a crystalline structure, a geometrical repeating pattern, which is what we call a crystal. You have the positives, the partial positives, or excuse me, the full positives, and then the full negatives. Just to show you guys an example, again, let me slide up here. So you notice this right here, that's a crystal structure. You have the positives, the negatives, in a very repeating, very organized manner. If I was to smash that with a hammer, the green and the purple would break apart and you would be left with basically a powder. So they're brittle because they could break along those lines. So all the positives and all the negatives, they could fracture and split along those weak points. All right, why are ionic compounds solid? Again, for this exact same reason, the structure is a crystalline structure. Okay, this is not true of covalence. So again, that's why they're let me put a slash on there. Atoms are held in place. Okay, that's a little different than the metallics, right? Because the metallics, if you hit them hard enough, they will move just ever so slightly, and therefore, again, that will change the shape. In the ionic, if you try to smash it with a hammer, it won't bend, it won't move. They're not malleable. It'll just break and fracture. Okay, that's because the atoms are fixed in a very particular location, and they do not have the ability to move at all. All right, so why do molten ionic compounds conduct electricity? Again, this is referring to this right here. Molten ionic compounds can conduct electricity because the ions are free to move. So remember, if it's in a solid state, then the ions of an ionic compound are fixed in place, right? Again, we just discussed that right here. They're fixed in place, therefore they cannot move. They cannot conduct electricity because nothing can move. Electricity, remember, is the movement of electrons from atom to atom to atom to atom to atom. In an ionic, they're fixed in place. There is no movement whatsoever. But if I put that ionic compound into water and it dissolves, all of a sudden now they come apart and they're free to move. They've dissociated. They've separated. Now the electrons can start to move and they conduct really well. You guys hear about like those energy drinks like Gatorade and Powerade. They all talk about electrolytes and how great electrolytes are for you. Well, electrolytes are important, but basically it's just salts. It's just ionic compounds mixed into your drink, and that's what's going to conduct electricity. Electrolytes are compounds that will help conduct electricity in your body. Okay, guys. That was kind of long, but that's a lot of information. So that is a comparison and contrast of the three main types of bonds we're going to discuss in this class: ionic, covalent, and metallic.